Good morning and thank you for watching my presentation about the project that I lead, which is about the fabrication of a multiple heater sensor platform for cell temperature monitoring. I'm Alexandra, a researcher at the LTM in Grenoble, France. So in this project, what I want to do is to be able to do non-invasive and regular monitoring of an in vitro cell culture, especially for rare cells. The solution that I present consists in controlling the temperature of the cells and doing at the same time live imaging of their growths. So I will use a substrate. On top of it, there will be a module that allows for local thermal regulation, and the cells are placed on top of it. I'll also have underneath all of this platform, an optical module that will allow me to do observation. The expected outcomes that I allow from this is to be able to maintain the optimal environmental condition at all time of the culture cycle, and so that the cells are not disturbed and can grow in the best way possible. Also, thanks to this, you will reduce human handling, and so you will reduce the harm you can do to the cells, and therefore limit any change in behavior that they could have. Here is a look at the state of the art. I've started the solution as function versus the active area size, which is where the temperature is regulated. Here are the commercial solution right now. So usually when you do cell culture, you use an incubator, which is a bulky equipment in which the temperature is regulated at 37 Celsius and you have the right composition of gas for the cells that you are growing. When you want to look at one of the culture, you just take it out from the incubator, put it at the room temperature, do your observation, and then put it back at 37 Celsius. This radical change in temperature will could induce change in the behavior of your cells, or even cause their deaths, which could be quite problematic if you're working with rare cells like embryo, neurons, or things like this. And so there are some commercial solutions in which you either bring your control environment to the microscope, or you bring the microscope into the control environment. All the solutions are nice, they work, but they are quite expensive. So some research teams are working into reducing the size of this platform. Some are only doing temperature regulation, and some have already doing both function of temperature regulation and optical observation at the same time. What I propose here is to reduce the size of the platform and doing both functions at the same time. Therefore, by using microtechnology, size should be reduced, and therefore also expected is the cost to be reduced in order to improve the adoption by the biomedical community. The choices that I have to do when starting the microfabrication were related to the constraint that I had. First of all, I had to have a transparent platform in order to be able to do optical observation. So I've chosen indium tin oxide as the heater material for my heater resistance. Then I wanted to have a high sensitivity for the temperature detection, so I've used platinum for the thermoresistive temperature detector, that is the platinum sensor. And then the electrical insulator in order to avoid any electrical shorts between the ITO heater and the platinum sensor. I've used silicon nitride, so it also allows the thermal flux to go through. The steps that I've taken during microfabrication, I've started with an ITO coated glass slab, and then I moved on to etch the ITO to form the heater pattern. Then I've sputtered silicon nitride interlayer twice as thick as the ITO heater, so that I could be sure that it was neatly covering every ITO. Then I've evaporated platinum to make the sensor and covered it all with silicon nitride in order to protect all of the system. Here you can see a photograph of the final platform with 4 heater sensor microsystems, each of them being identical to the other. I wanted to know what was the temperature distribution, so I've done numerical modeling using the finite element modeling software that is ANSYS. I've used steady-state thermal electric conduction as a multiphasic module, and the geometry that I've drawn is an ITO heater on top of a glass substrate and everything surrounded by air. The design of the heater that I've selected is a meander-like structure with 15 micron wide lines in the active area where temperature is regulated, and otherwise all the track lines are 100 micron wide. And the active area that I've designated is 500 micron side square. Here you can see the result in terms of temperature distribution. As expected, it is hotter in the active area, and all of the track lines and the electrical pads are less hot, almost at the room temperature. Therefore, this is where I wanted to confine the hot temperature, and this is what I obtained. Here you can see the temperature as a function of the x-axis, this line, and it is 100 micron wide in each direction from the center. It is twice as big in the y-axis, and the 37 to 36 Celsius region is 70 micron high in the z direction, meaning that this 36 to 37 Celsius region is wide enough to grow at least 1 layer of cell. Then I moved on to do the platform characterization. In the normal behavior, what I will do is to inject a current in the heater resistance. Through dual effect, the temperature will rise, and thanks to the conduction through the silicon nitride, this will also heat up the sensor, which is a thermal resistance. Therefore, if you measure the resistance, you should know what is the temperature. So you need a two-step characterization in order to know what are the nominal conditions of your platform. So first, you have to characterize the sensor, meaning establishing what is the relationship between the resistance and the temperature. Then I have done the characterization of the heater, doing the relationship between the current that I inject and the temperature that it is at. So first of all, the sensor characterization, I placed the platform into a temperature regulated furnace and inject current in the sensor using a source meter. I've injected 15 microamps input current and measure what was the resulting voltage. Then I plotted the resistance as a function of temperature and done a linear fit of this relationship. You can see here that this is very linear, and so I could know what was the resistance at 0 Celsius, and alpha is the temperature coefficient of resistance, and the value that we obtained was close to what you can see in the literature for platinum. thin films. Then the heater characterization consisted in using one source meter for controlling the heater and a second source meter for controlling the sensor. I've gradually increased the current injected into the ITO heater and extracted the temperature through the measurement of the sensor. I had to go up to 6 millionths of current into the heater in order to reach 37 Celsius in the platform. Then I've done thermal characterization of the platform. First of all, a qualitative mapping of the emissivity was done through lock-in thermography. So you have to be cautious when you do this kind of mapping because you can only compare similar material between them. So here we look at the ITO tracks here, and what we can see is that the ITO is hotter in the active area like the numerical modeling was predicting. If we compare platinum, we have platinum here and platinum here. So what we can see here is that the platinum is also hotter in the active area. So this is the full view of one heater sensor microsystem, and this is zoom in the active area. So the thermal imaging confirms that the heating only occurs in the active area. Then I moved on to do quantitative infrared thermography. In order to know what was the absolute temperature, you need to do first an initial calibration. So this is a pixel by pixel calibration. You place your platform on the thermal chuck at 25 Celsius and you do an emissivity map. Then you heat up the thermal chuck to 45 Celsius, wait till everything is at 45 Celsius, and you do a second emissivity map. Thanks to all of this pixel by pixel, you can know what is the absolute temperature of your platform, whatever material you have. So we've done this, and this is what we obtain using a 10x objective in the active area. So you see that yes, it is at almost 37 Celsius when we were doing using the nominal current injected into the ITO heater. And if we compare to what the ANSYS numerical modeling was predicting, we can see that they agree one with each other. So this was a really nice result to check that we were actually getting what we were expecting to obtain. Then I've done, I wanted to validate that I could have a bifunctional platform, meaning that I wanted to heat to regulate the temperature in the active area and also be able to image what was occurring on top of it. So I've used a commercial CMOS imager, Hypersense, and at the same time I was injecting the nominal current into the heater and the sensor in order to have a 37 Celsius temperature in the active area. And this is what I could image in this region. So you can see here the ITO tracks, the platinum tracks, and the protective layer here of silicon nitride. And what we were using to image were 100 micron diameter polystyrene particles, which diameter were chosen to be close to the size of the cell we will be using later. And if we compare this to a macroscope view of the exact same area, we can see that, yeah, we were able to image this particle quite nicely, actually, meaning that the platform is transparent enough to image what is on top of it when you place the CMOS imager on below it. So the bifunctional platform was validated, and we're able to image while heating. So in conclusion, I've shown you that I've been able to microfabricate a multiple heater sensor platform that will, in the end, be for in vitro cell culture and to monitor their temperature. I've been able to check that the numerical modeling of the temperature distribution was identical almost to what the thermal imaging measurement had given us. And the heater sensor platform is transparent enough so you can do live imaging of what is happening on top of it. The next step of this project will be to add a microfluidic stage on top of it in order to do cell perfusion, and so we can test for in vitro culture and validate this platform. I'd like to acknowledge the help of the PTA platform in Grenoble for the microfabrication, the help of Gaëtan de Bontride for the electrical characterization of my platform, and finally Denis Blachier for the thermal characterization of the active area. Thank you for listening, and I will answer any questions that you may have.